Okay, so both of the clocks seem to think it's time to start by now. So our first speaker this afternoon is Harald Helfgott from Paris Set. And the diameter of the symmetric group ideas and tools, or shorter version of the title that's up there.
So I'm actually, many of you have been asking me, I am on leave from CNRS right now, so right now I'm in Göttingen, but for some reason the affiliation, it's not incorrect, but there's slightly mistakes. Very well. So Cayley graphs, for some of you know them better than I do, but I still think it's, yes? What about the microphone? Oh, I see. All right, thank you. Let me still go over the notation. So Cayley graphs are, for me, they are. I'm not going to do any sophisticated geometric group theory. Though if you see an interpretation of this in terms of highly sophisticated geometric group theory, please tell me. I'm very interested. For me, Cayley graphs are just a convenient way of thinking about problems. So a Cayley graph is, of course, just a graph in which you take a group and a set of generators, and you draw a vertex for each element of the group, and you're going to connect two elements in the group, two vertices, if their quotient is an element G of the set of generators. Actually, I should be consistent. So, since I'm going to deal with permutation groups, I'm choosing to write things this way. So G is an element of the group, A is an element of the set of generators. All right. And everything will be non-oriented. And you can think of sets of generators as being chosen to be symmetric. So A equals A inverse. If that's not the case from the beginning, you just include all inverses of your generators in the set as well. So the diameter of the Cayley graph can be defined to be simply to be the diameter of the graph. No? So again, this is something that most of you know better than I do. But you define the distance between 2 points in Cambridge, say, not as a Euclidean distance, but as the length of the shortest path between them. And then the diameter of Cambridge is the maximum over all pairs P1, P2 of the distance from P1 to P2. That's the distance in the diameter of a graph. The diameter of a Cayley graph in particular, well, it's a special case of that, but it's easy to convince yourself that it's the same as saying, well, since my set of generators is a set of generators, I can express any element of the group as a product of elements of the set of generators. And you ask yourself, well, what is, for each element, I consider the shortest possible word, and what is the longest shortest word? How many, what is the smallest k such that every element of the group can be written as a product of at most k generators and their inverses? All right, so just setting the notation. Of course, diameters can be very small. They can also be very large. If I have Z mod n Z, and I have the set of generators 1, or 1 comma minus 1, then the diameter of the graph is n over 2. No? So in general, if G is abelian, or if G is nilpotent, then it can be the case that the diameter of a group is very large, as in a power of its number of elements. But when that's not the case, when G is not abelian, or close to abelian, it does seem to, people started realizing about a generation ago the diameters tended to be quite small, at least experimentally, and it was quite hard to come up with counterexamples. So people started wondering, is it the case that diameters tend to be quite small, or even have to be quite small, when the group is not abelian? So in fact, you could say that non-mathematicians started realizing that, and that non-mathematicians started to make puzzles. And the very idea of a puzzle is that even though there's an enormous number of possible combinations, there is always a solution of reasonable length, provided that the problem is solvable at all. Unless unless the puzzle is really, really extremely stupid, such as you have an enormous wheel and you can turn it around only a little bit. No? All right. So in the case of Rubik's Cube, that's a case in which the diameter is very reasonable compared to the size of the group. We will not really care about the fact that it's 20. We just care about grosso modo sort of bounds, asymptotic bounds. So define the diameter of the group to be its worst case diameter. So you take the maximum of the diameter over all sets of generators. So you choose the worst possible set of generators and you consider the diameter with respect to that. So is it the case that that's small? So is it we're asking ourselves, we're asking for bounds that upper bounds on the diameter, even if the set of generators is chosen by your worst enemy. So there's this general conjecture due to Babai, which says that if G is the very opposite of abelian, so if it's finite, we're dealing with finite groups here, simple and non-abelian, does that imply, well, sorry, the conjecture is that that implies that the diameter is a power of log. C is an absolute constant. So this is known for, by now, many families of groups. So I mean, my work on that was the first for any infinite family of groups. So I proved it for PSL2P. Well, then Dina and Varyu, who were quite young at the time, I generalized it to other fields, and going to higher rank turned out to be quite complicated. So you have the entire history there. The point is that by now, people know this for, say, SLN n bounded, or rather for SLN, general n, but the quality of the bounds depends on n. And also for SON, for matrix groups in general. People know this. The dependence, there is essentially no dependence on the field, or rather, just affects the size in the way that is predicted by the conjecture. But the dependence on the rank, on n, or n minus 1 rather, is not so nice. In fact, it's really not nice in some cases. So there are two things we don't know. How to get bounds on the diameter that still obey the conjecture we see independent of n, of the rank. And the other problem is, well, what about groups that are not matrix groups? And by the classification theorem, I mean, so you have, of course, three kinds of finite simple groups, finite simple non-abelian groups. So you have the matrix groups, you have the permutation groups, well, basically just all 10. And then you have the monsters, but we don't care about the monsters because there's only a finite number of them. So we put them in a zoo and we forget about them. As I said, we care only about asymptotic statements here. So the big open case here is AN, and there's also the dependence of the case SLN on n, but as different religious sects tell us, AN is SLN over the field with one element. So the field with one element is this mystical entity. Either it doesn't exist or people have different beliefs about it. However, don't overinterpret that. However, people do tend to agree that SLN over the field with one element is AN. And
I'm sorry.
yes.
For a solvable group, the diameter of polynomial order?
It can be. It's a bit of a tricky issue. We can talk more about this later. It's not the main subject of the talk, but it's a case we understand well. So a case we understand well. In fact, it's very close. It's very close to what people call the sum product theorem. In fact, the sum product theorem is a special case of it.
But it's depending on the family. There are families which is logarithmic. It's not necessary.
Well, it depends on the I would say it really depends on the set of generators. Yes, but yeah.
Family.
But you can, in general, in a solvable group, you can have that. We can talk about it. It's really a different flavor of thing. It's something intermediate between nilpotent and simple. But at least we understand it fairly well. But in some sense, this is not quite the right question. And if you frame the question in a different way, then you can give a rather clean statement. There are still some things we don't know. So here I'm focusing on simple groups. All right. So, well, you all know what AN is. It's just a subgroup of index 2 in Sn. We focus on AN because it's simple. So, all right, that's what I just said. All right. So there is one bound, or rather, there used to be a bound that was much worse than this due to Babai and Seress from more than 30 years ago, exactly 30 years ago. They showed that the diameter, the worst case diameter of the alternating group is at most e to the square root of n, basically. And then Seress and I showed that it's actually e to a power of log n, in fact e to the log n to the 4 plus epsilon. So, all right, it's what's called quasi-polylogarithmic. No, quasi-polynomial on n, quasi-polylogarithmic on the size of the group. All right, and this actually implies that the same is true for any transitive subgroup of Sn. Though again, here, see the the dependence on n is the same. The group may be quite a bit smaller. The corollary follows from the result and an existing result that uses a classification. And I should give this allergy warning that the known proof of Helfgott Seress, the proof that we gave, does use a classification. But I should take a step back and talk a bit about what I did back in the day in SL2 and the basic idea carried over to SLN and to other groups of Lie type. So for me the main result was really the product theorem, and then the diameter bound was a direct consequence of this. So all right, so I showed that, and this is already the general statement for other groups of Lie type. So, but I showed that if you have a subset A of SL2 over a finite field, or over Z mod PZ, what have you, then if you take A times A it was known that A times A may be barely larger than A, but I showed that A times A, so A cubed, so the set of all products of 3 elements of A, and we'll be very clear about this. Again, it's very basic notation, but not everybody uses the same notation. So that set, A times A, must be much larger than A. Its number of elements, that's what's meant by vertical bars, must be larger than the number of elements of A to the 1 plus delta, where delta is positive. No? So, there. All right. So, in order to prove the diameter bound, you just apply this again and again. So A cubed, you take a set of generators A, so A cubed has to be quite a bit larger than A to the 9th has to be quite a bit larger than A cubed, A to the 27th has to be quite a bit larger than A to the 9th, and after log steps, you must get something as large as the group itself, or well, it cannot be larger. And so this has to stop being the case, so you must be in the special case where you have reached the entire group. And so the diameter is bounded by a power of log. All right. And which power? It's just the inverse of this epsilon. Should be a delta, but never mind that. Now, the problem is that even though Babai's conjecture is still believed to be true in its original form for the alternating group, and also for SLN without any dependence on n, other than, the dependence that comes from the size of the group, this sort of product theorem is false in the alternating group and also in SLN for n unbounded, because you can have a set S like this, where, yes, so it's rather easy to describe, and you have that S cubed is barely larger than S. By barely larger, I mean S times a polynomial on M. Yeah. And it's known exactly how strong, let me see. No, actually, we don't know exactly how strong the dependence has to be, but we do not know. We do know that there has to be a dependence on the rank in a product theorem. Whereas in Babai's conjecture, which is still believed to be true, there should be no dependence on the rank. And that's not the only problem. It's also the case that the main ideas that go into the proof of the product theorem in SL2, in SLN, do not, I mean, it seems hard to even give any meaning to them, because they really rely on the concept of variety, dimension, and so forth, things that don't really exist in any traditional sense in the alternating group. So I will explain what is meant by a dimensional estimate, but basically it's bound. So if you have a set A and you assume it barely grows, well, we want to show that sets that barely grow and generate the group do not exist or are the entire group. But we start by showing that they must be really quite nice, quite so nice that eventually you get a contradiction. But so what do I mean by nice? I mean that its intersection with varieties of given dimension is roughly what you might expect out of dimensional considerations. I will talk more about that. But in AN, in the alternating group, it's unclear even what the dimension of I mean, what sort of set would be algebraic and what would it be, what would its dimension be? I do not know, maybe somebody knows. And there's also the idea in SLN, and this is closely related to dimensional estimates, that you can escape from some variety. So that was already known over the complex numbers, groups over the complex numbers. The same techniques turn out to work over finite fields. You say that you don't like matrices that are special in some sense. Say they have repeated eigenvalues. Well, you can say, well, sure, we don't like those matrices. Perhaps my set of generators is made exclusively of such matrices. However, because it's a special condition, meaning matrices that have repeated eigenvalues lie in a variety of positive codimension, there is a general result that tells you that even if A is completely within that variety, A times itself a couple of times must have elements outside that variety, in fact quite a lot of elements. So just in a couple of steps you escape from the variety, you escape from a special condition. But again, in the alternating group, it's completely unclear a priori what would it mean to be special, what would it mean to lie outside a variety. Again, maybe some people can come with a general concept of that sort, but then I would like to hear about it. And I would really like to explain that I am really interested in product theorems. Well, my interest, the reason why I formulated things in that way was that I started from additive combinatorics. I was trying to see how things would work in non-commutative groups in general. But other people also care more about, there are people other than myself that care more about product theorems than about the diameter bounds themselves. That's because, well, Brugan and Gambert, quite soon after my first results, managed to give a proof of expansion. I will not go into the details of what expansion is. Again, many of you are experts. If you're not, it doesn't matter. But the point is that saying that a graph is an expander is a stronger statement than saying that it has small diameter. And it turns out that if you put a product theorem together with other tools in a non-trivial way, you get that you get, in many cases, a proof of expansion for many sets of generators. So let me tell you what my goals are in this talk. And I should make clear that aims here means neither fulfilled nor unfulfilled aims. This is work in progress. Well, I would say 2 is fulfilled by now, but I would like it to be a bit stronger. So, and possibly 1 as well, but I'm still trying to polish things up. Those, I can say truthfully that they are fulfilled. I would like to fulfill them a little bit better, perhaps. And Laszlo Piber is working on 4, but 3 is really unachieved, I should say. I should not claim anything there. So goals 1 and 2 are simply to give a better proof of Helfgott-Seress. And what do I mean by better? Not just shorter and clearer, but my goal was to unify the proof there with what I had done before and what other people had done before for matrix groups to the extent possible. And that gives in particular a weak product theorem. It cannot be a strong product theorem in the sense of SLN, because that would be false, as I said. All right. And Piber is working on removing the dependence on classification. So this is, yes, so well, that's, the dates are actually true, namely this dates back to last year, but the paper is still in preparation. so I have managed to give a somewhat weaker sort of product theorem. So instead of having that a cubed, a times a is larger than a, I have that a to a power that is n to a constant is larger than a. And by larger or much larger, I don't mean a to the 1 plus delta, but rather a to the 1 plus something that goes to 0 but really slowly. So it's actually larger than 1 over log n squared. In practice, it's like 1 over log n. So either that happens, or what do you have? Not quite that you have reached the entire group, but rather that you can reduce matters, you can reduce the problem to the same problem over a significantly smaller group. And that allows an inductive process. All right. Yeah, so a smaller, or rather a group made up of smaller pieces. And the immediate corollary, again, via this result of a recherche, this is a classification, is that you have that the diameter is at most log n to the 4, e to the log n to the 4 times log n squared. So this is, so I've succeeded in making Helfgott Seress very slightly worse. So there's a log n squared here now. I think that the squared can be removed, but then the proof will become more complicated, and that's not really my aim here. All right, but what made me quite happy is that I could give at least a partial analog of dimensional estimates in AN. So first, let's go back to matrix groups. So what do I mean by a dimensional estimate? So I mean that if you take a set A of generators, and well, I'm giving the special case that I had back in the Middle Ages, but this has been generalized to any variety in any group of Lie type. Here it's given for finite groups, but K does not even need to be finite, in fact. But so let V, A needs to be finite for this to make sense, but K doesn't have to be. So let's say that you have SL2, which is this three-dimensional thing, and you have a one-dimensional variety. It would be quite useful to have a blackboard pointer of some sort. Well, so instead, let me talk about a two-dimensional variety. So let me see that I have this.
There are pointers lined up against the thing right now.
Excellent. So A is this sort of blob, right? My set of generators. And then I go like this. And the point is that if either A grows rapidly, and we are done, so either A cubed is quite a bit larger than A, or A is highly regular in the sense that however I stab it, this way, or that way, I mean the blood or ectoplasm here will be about of size A to the 1/3. So it's really a blob in that sense. A very regular sort of blob. Yep, so that's the dimensional estimate. In order to try to generalize this to alternating groups, I first take a step back and try to give a statement that has no dimension or geometry in it. It would be this. So here I'm stating that if I have, in any abstract group, if I have R and B in this sense, either you have that conjugating R by the elements of G and then multiplying that by itself gives you something substantially larger than R, or the intersection here has to be large. The intersection of the conjugates has to be large. So that's actually quite easy to prove. It's just basically an exercise. But then what can you do? The aim is given R and to choose or to work with a B such that you manage to make the denominator here trivial. So when that is the case, then you just have that the thing in the left is at least R to the 1 plus 1 over K. Now, how can this be used to prove the statement that I acted out here? Well, the point is that you can think of, so in R here, would be the intersection, right, with this one-dimensional thing. And then B is going to be composed of fairly generic elements that send this in 3 independent directions, right? And the intersection of the line with 2 conjugates of it in generics, no, the simplest way to explain this would be if I actually had a plane, but never mind that. It also works with products. This all can be shown. You can go in either direction. Using that, you can do you can use you can show how to prove the statement here using the following procedure. So you really conjugate this in 3 independent directions. Instead of taking intersections, you take products. It's all equivalent in the end. And you are going to have, since these are 2 independent directions, you are going to get something that is of size, that's right. You're going to get a product that is of size about the cube of your intersections. And if the intersection here is too large, then you are going to get something that is larger than the cube. So if the intersection is larger than what it should be, so larger than the cube root of A, then the product of the intersection with 2 of its conjugates is going to be substantially larger than the cube of the cube root, so substantially larger than A. That's the basic idea. No, and this all works out because of this inequality here. All right. Now, the notion, so what is special? I was talking about what special meant and what escape from varieties meant. Now, the point is here that if R is special, then you are going to... So the geometric sense of special is clear, but here special will mean simply that something is special if its intersection with generic conjugates is going to be trivial, provided you take enough conjugates. Now, what could that ever mean in the case of alternating groups? So one particular meaning you can give to this, and this is inspired by work from the early 80s by Babai, is that you can take special to mean having no very long orbits, right? And then it's actually quite easy to show that if you have a set without very long orbits, orbits can be defined not just for subgroups, but for sets. Then, if you take the intersection of that with a logarithmic number of conjugates, picked randomly, and that would be the sense of generic here, just random, the outcome of a random walk, perhaps, or what have you, then you are going to have a trivial intersection. And so you can apply this abstract statement here and get this. You get the following, that if you have that R squared, you have a set R, you have B generating, B can be quite small, but it must generate a 2-transitive group. So if R squared has no long orbits, then the multiplication of a few conjugates, just basically 2 units of conjugates of R, is going to have to be substantially larger than R. Very well. Yeah. And where does this magical number n to the 6 come from? It's because you take some random walks. And if you take a random walk of length n to the 6 on an alternating group, even with really bad generators, that's going to scramble all elements and all pair of elements almost uniformly. So again, this can be put in the as in the previous case, but this statement can be used to reformulate entire proof of Helfgott-Seress. And this statement, as I showed, is really just a consequence, is a special case of the statement for abstract groups that also gives you the dimensional estimates that is at the basis of the proof for linear algebraic groups. So now let me go back. Let me try to set up the proof for the alternating groups. And even though the proof is not computational, it doesn't give you, we don't know how to navigate Cayley graphs well, even to this date. There is one nice paper by Larsen for SL2 for one set of generators, but in general we don't know how to do it. That is, we have all of these diameter bounds, but we don't know how, if you give me a set of generators and an element of the group, how to find a short word in the set of generators for the group. So we know now that there are good solutions to just about every puzzle, but we don't know how to find the solutions. However, I found that knowing some of the theory of computations over alternating groups or permutation groups is actually quite useful. Some of the ideas there turn out to be very useful for proofs of diameter. And I will explain exactly why, even though the proof is not itself computational. But let me tell you right now just what is one basic idea, one basic structure that is used in the proof. It's just a notion of a chain of stabilizers. So you first take a group, G, or a set A, and then you consider the subset that consists of the elements that leave one point fixed, and then the even smaller set that leave that point and another point fixed, and then the even smaller set consisting of things that leave those 2 points and a third point fixed, and so on. So you have this chain here of inclusions. Yeah, and when I use parentheses here, I really mean the point-weight stabilizer. So the elements that leave every single point here fixed, rather than the set-weight stabilizer, which consists of the elements that permute these elements, possibly trivially. All right, so we choose this chain of stabilizers readily, so that at each step the orbit is of maximal size. And this again is a bit like what was going on in a proof by Peter of a different statement in the 80s or early 90s. All right, so we do that. And we stop when there is no very long orbit. So at each point, given our set, we choose an element that is part of the largest orbit, and we stabilize that, and then an element of the largest orbit of that, and we stabilize that, until we find that there are no really large orbits. And so what happens then? Well, by the special set lemma, either A grows and we are done, or this point-weight stabilizer must be sort of smallish, right? But however, the only way, by pigeonhole, the only way this can be smallish is if J, the number of points being stabilized, is fairly large. So, well, let's say that we are in that case. So we have got a long stabilizer chain such that even though it keeps decreasing in size, every element of the stabilizer chain has a long orbit. And that gives us, it's actually quite easy to see, that the set-weight stabilizer, when you project it to the set, to these sets of elements that are gradually being stabilized in the chain, must be quite large, and in particular generate all the rest. So let me really draw this again. It's convenient to think of these, yes, you might as well call them 1, 2, just like as you could call them Pete or Mary. We will just call them 1, 2, K, these elements being stabilized. And so what we have is that, well, when you stabilize them all, there are no long orbits left, but when you forget about the last one, and so let's call that one K, then you still have a long orbit, a really long orbit. And moreover, if you just stabilize this set-wise, so if you allow, if you consider elements that send these points to each other, but not necessarily to themselves, then, and then you project to here, to what we might call the prefix, then you get not just something that generates alt n or sim n, but something that is a really large subset of alt or sim here. Yeah, that we call the prefix. All right, and the point-weight stabilizer restricted to this set here, or rather to this, the stabilizer of K and the last point K plus 1 is here, that's called the suffix. And you have that the statewise stabilizer is acting on the suffix by conjugation. So let me give you, all right, so everybody today has been making the link to the conference title explicit. So let me tell you what the link here is. People have been talking over the last few years about what they call approximate groups. So in particular, there's a word, that's an expression that Green, Briere, and Tao really like. It's a nice expression, but it's not really one that I use so much. In part, well, I was just speaking before about sets that grow rapidly, and it seems to me to be a more down-to-earth expression, but it's also the case that gradually I grew to see the basic operation not as being really group multiplication, but really more generally what I realized I was doing was studying actions. And these are actions induced by group multiplication, or in some cases it's something that we use as a tool to study something, and it's really something more, something that is in our heads. But at any rate, it's the action that is causing, an action in general that is causing the group. And we should be thinking of structures that are approximately invariant and their actions, and their group actions. In this case, it's the action by conjugation. So the setwise stabilizer acts on the pointwise stabilizer by conjugation. And you can ask yourself, well, is it making the suffix grow? All right. Very well. I think this is exactly the tone of red used in the side of some serial boxes for similar reasons. Very well. So the suffix, by assumption, has no really long orbits. But what about the group generated by the setwise stabilizer? If it had no long orbits, then you would have a reduction to smaller groups, and that's precisely what the weak product statement was saying. Now you have this prefix there. It contains, by a null result by Wieland, it must contain, because the prefix contains a large alternating group, that means that H contains an element of small support. But then what happens? Because the diameter of H would be relatively small by induction, you will be able to construct that element relatively rapidly. But as soon as you have, it was known that as soon as you have one element of relatively small support, you can construct everything very quickly. In fact, that's even, I really do mean construct as it happens. The diameter becomes polynomial in size. And so we will be done. So, in fact, you can assume that the group generated by the setwise stabilizer has a long orbit. And in fact, it acts like alt-m or sim-m on it. So you have something without long orbits living in something with long orbits. In fact, something that contains am or sm. But that means that we are in, again, in the case where we can use a special set lemma. No? So if you have alt-m and within it a set without long orbits, then the union of that set with a few conjugates, in this case conjugates by the setwise stabilizer, is going to grow rapidly. And we just do that. And there is, so you get that just the product of S with itself a few times is considerably larger than S. Well, and then there's this basic lemma that growth in a subgroup is inherited by the group. So if multiplying S by itself a few times gives you growth by a factor of S to the 1 over log n, then multiplying the original, any of the original sets A in entire symmetric group by itself is going to have growth by about that factor at least. So we are done unless S happens to be very small, in which case compared to A. No? So if S were comparable to A, or comparable to, say, the 10th root of A, we would be done. So the only way we are not done, we could fail to be done, is if S were quite small. But how can we force S to be not so small? Well, again, it's a matter of growth being inherited. If we show that the product of A with a few things must have not so few elements in the point-weight stabilizer, and that turns out to be substantially larger than S, then growth by that factor is inherited by the group. And if it's not substantially larger than S, then S was not so small to begin with. So what can we do? We can just, we have these generators of all time here. They may be a large set of generators, but it's not hard to show that they must contain, or the product of that with itself must contain just a few elements that generate a large transitive subgroup of all 10. But then that means that, well, if you commute with a set of generators of a large transitive subgroup, that means that you commute with the entire subgroup there, so you must fix those elements pointwise. So you must be an element of small support, and you are done, as I said a slide ago. Assuming that that does not happen, then you have that the prefix acts non-trivially, any element of the prefix acts non-trivially on at least one element of that really small set of generators. But that guarantees then that at least one of the generators must have very many distinct conjugates when you conjugate it by the prefix, or when you conjugate it by the set S, rather. And that's how we obtain growth. And this is where that factor of log n was coming from before. And that's it, really. So that's a sketch of the proof, but I have not omitted that much. So it has really become significantly shorter. And I should, in my remaining time, I should just tell you the moral of the story. Things got a little bit technical. Maybe some of you started to sleep, or no, my glasses. Well, so now let me. I briefly alluded to the religious problem of the field with one element. Let me not talk more about that. But rather let me give you a small sermon, but it's going to be a strictly secular sermon about what the moral of the story is. So something that became clear already in the days of SL2, SL3, but is even clearer now, is that many statements in group theory of the sort that you would teach undergrads, so very concrete statements, do carry over, not just, they are usually stated for subgroups, but they are true for sets if you state them correctly. So, for instance, so it sounds completely insane, but say the orbit stabilizer theorem, it's a very simple statement, it's really a lemma, a basic lemma, but we call it a theorem when we teach undergrads. That's true for sets as well, if you state it right. It's no longer an equality, it's two inequalities in different directions. They are slightly weakened, but they give you the original statement in the special case where the set is a subgroup. And yes, so and that's a statement about group actions in general. So the sub-moral there is that if you have got a statement that has a very concrete quantitative proof that may carry over to sets. Before I talked about computational results, now including really old results from 100 years ago, back when people were doing group theory with their bare hands. And there again, if you've got a procedure, then the thing might carry over to sets, not just subgroups. Why? Well, in the case of sets, we do care a great deal about diameters and so forth, but if your procedure was sensible, its number of steps was bounded, and if you're lucky, the length of the products that result from that also have reasonable length. And so you're going to be able to get sensible results that are not too expensive in the sense of not involving words that are too long. And those results will be useful for you, even if you're not trying to give a constructive solution to the problem, even if you're just trying to show existence. And there is also what people in combinatorics love to call the probabilistic method. It's not really just one method, it's some sort of general philosophy. So you want to show that something exists, and in order to show that something exists, say, you want to show that there exists an elephant in Cambridge, and what you show is that if you pick a random animal in Cambridge, with positive probability it will be an elephant. Hence, there is at least one elephant in Cambridge. Now, we cannot really afford to do that because we want to prove, I mean, that will be assuming what we're trying to prove. We're trying to prove that Cambridge has small diameter. So we cannot just teleport ourselves to any random place in Cambridge just like that. However, if we manage to show that a short random walk in Cambridge makes us find an elephant with positive probability, then that does help us. That does show that elephants exist in Cambridge, and that moreover there's a short path to an elephant. So that's a stochastic analog of the probabilistic element, if you want to be a probabilistic method, if you want to be a bit pretentious. And that sort of thing sounds like gobbledygook, or just like some sort of dream, but it does work. And that works because you have this large group whose diameter we're trying to bound, but there's one nice thing about it. Even though it doesn't have this nice geometric action that SLN has, it does have a nice property in that sense that it has these really non-trivial actions on really small sets, such as the set 1, 2, up to n. So just a set of n elements whose action defines the group. All right, and it is that allows us to give subset versions of results by Babai, by Piber. That was the case already in the original proof of Helfgott and Seress, and that now is just a corollary of what was I saying before about the special set lemma. It's also useful to use previous results in the literature about all 10, of course, but you can actually rephrase some of these things in these terms. Well, in fact, you don't even need to rephrase them in the sense that Babai Bill Seress, BBS here, is stated, I mean, the proof does go through random walks. And again, what is crucial there is that because it's an almost immediate consequence of the fact that the set with n elements is small compared to the size of the symmetric group on n elements, that already tells you that with respect to any set of generators, a short random walk will scramble those n elements. So yes, I've really got a bit moralistic here because there are more morals. So there are actions that are worth studying for every group and that you can study for every group. There's the action by multiplication on the left, on the right. Well, those are boring, but once you take quotients, they stop being boring, and they give you things such as what I said before, that if you've got growth in a subgroup, you can lift that up to give you growth in the group. Or when you have got growth in a quotient, you can also lift that up to growth in the group. Now, what is even more interesting is to study the action by conjugation. That's really what makes entire clockwork click, both for SLN and for Siemens. To study the action by conjugation, because that has non-trivial and really interesting orbits and stabilizers. Orbits and stabilizers. So that gives you, the stabilizers are commutators, and the orbits are conjugacy classes. And you get to bound the sizes of conjugacy classes, and that really makes things work. Now, besides that, so those are the things that you can actually build up from just multiplication in the group. But then, in order to understand your sets better, you also study other actions. And then, what kinds of actions you study, that really depends on what kind of group you're working with. So in the case, and the actions that turned out most useful to study are the type of actions that really define the group and tell you what kind of group you're working with. So in the case of a matrix group, what are matrix groups? Matrix groups are things that are acting on Euclidean space. No, just k to the n, affine space. And the nice thing about that action is that it's geometric. It sends planes to planes, it sends varieties to varieties. It doesn't change the dimension, it doesn't change the degree of things. And that turns out to be crucial. But in the case of all 10, what you have is a much less structured action, but as I said, the crucial thing there is that the thing you're acting in, whether it's the set of n elements or the set of pairs of elements of the set with n elements or what have you, those sets you're acting on are really quite small. And that helps you. That's what makes the short random walks argument work. What makes you able to catch elephants quickly. And that's it. And I think I've succeeded in making everybody free to to go to tea time at the appointed time or even 5 minutes early. So I certainly welcome questions.
Do you have any questions? Plenty of time for questions.
Yes.
So your diameter is maximized over choice of set generator.
Yes.
So I wonder, I mean, for each of these groups, what is the generating set which maximizes the diameter?
That's a good question. That's hard to. I don't think the time for an answer. I don't know. I don't know what the answer would be. I think. All right. I can actually tell you. I wouldn't be able to even begin to give an answer in the case of matrix groups. In the case of the alternating groups, I can tell you at least that the culprits will be special in the sense that we can give much better bounds. Actually, no, that's also true in that sort of sense. It's also true for matrix groups. That random pairs of generators give you graphs with much smaller diameter. So already Burgan and Gambert showed that if you pick using my product theorem, they showed that if you pick a random pair of generators of SL2, the diameter is going to be in fact not a power of log, but log, or a constant times log. In the case of the alternating group, what I have is a paper with Seress and Zook, where we showed that the diameter is bounded basically by log of the size of the group squared. So we believe that the truth is probably log of the size of the group. That's a constant. But we don't know that. However, log of the size of the group squared, that's already a lot better. That's certainly polynomial. It's a square. So that tells you that if there are things that are worse than that, then they have to be rare. But what they look like, I have no idea. Other than the fact that, I mean, for instance, they must be generating sets, all of whose elements have large support. Otherwise, available share should apply. So each element of the set of generators must move, at least 99% or 90%, say, of the elements.
Another one.
Of
You
two
mentioned
sets.
is like algebraic group overfilled with one element.
Yes.
Can you say a few more words about that?
I could say several things. I'm very much agnostic about that. I don't want to take side in that sort of religious war. So, so, all right. Where would I even start? These theories tend to be pretty sophisticated, and I don't want to get into that. So you get all of these constructions over this field that does not exist. So basically, all right, the way that I intuitively try to make sense of that is that when you have no field left, you are left with a bare skeleton of the Lie group. You're left with a Weil group, and that's what. But I'm sure that this is really my naive take on this.
More questions? We see if we've surprised them and there's no coffee ready yet. Let's thank Harald again.